Next, we're going to look at an example of how we can use enthalpies of formation to determine the standard enthalpy change for an overall chemical reaction. This example doesn't come from the OpenStax textbook. It's an example I pulled from another source, but your OpenStax textbook contains a similar example where you use enthalpies of formation to determine a reaction enthalpy. In this problem, we're told that we can decompose glucose to give us 2 moles of ethanol and 2 moles of CO2. This is basically the process of fermentation that bacteria and yeast can perform on glucose. So the balanced chemical reaction that we're given reads 1 mole of glucose C6H12O6 in the solid phase breaks down to give us 2 moles of ethanol C2H5OH in the liquid phase and 2 moles of CO2 in the gas phase. We want to find the overall enthalpy change for this reaction, and we're given no other information. From a strategy standpoint, one of the challenges that we face now is several techniques for finding heat absorbed or released by a reaction and for finding the enthalpy change associated with a reaction. These techniques or these approaches are all self-consistent, but the strategy that you use should be governed by the information given to you in the problem. So for instance, it would be tempting to use Hess's law in the form that we just recently learned to solve this problem, but it's problematic because we're not given any other balanced chemical reactions with their enthalpy changes. If you are simply given a balanced chemical reaction and no other information, and you're asked what the enthalpy of the overall reaction is, the most direct approach is to use enthalpies of formation, which you can always find in Appendix G of your textbook or on the sapling information page for your homework to determine the enthalpy change of the reaction. So the signal for the correct approach is if you're just given a balanced chemical equation and you're asked what the enthalpy of reaction is, the most direct route is always going to be to use enthalpies of formation to determine the overall enthalpy change. On quizzes or exams, I would probably just give you the enthalpy change or the enthalpies of formation up front for you to calculate the enthalpy change. But our general approach here is, since we haven't been given any other information about enthalpies, we are going to use enthalpies of formation, which we can always find in a table, to calculate the overall enthalpy change for this reaction at standard conditions. So if you're dealing with enthalpies of formation, the overall enthalpy of reaction under standard conditions is equal to the enthalpies of formation for the products multiplied by their stoichiometric coefficients. And from that, we subtract the enthalpies of the reactants multiplied by their stoichiometric coefficients. So we have to identify our products, and we'll add up their enthalpies of formation first. And then from that, we'll subtract the enthalpies of formation of the reactants. The key thing is you have to remember the number of moles of each chemical matter. So if you're making 2 moles of ethanol or you're making 2 moles of CO2, you have to take that into account in your calculation. So overall, we can find the enthalpy of reaction for the fermentation process by taking 2 times the enthalpy of formation for ethanol. So the 2 comes from the balanced chemical equation there, plus 2 times the enthalpy of formation for carbon dioxide. And again, the 2 is the stoichiometric coefficient in the reaction. And from that, we subtract 1 times the enthalpy of formation for glucose because we started with 1 mole of glucose. To get our value for our enthalpies of formation, delta H naught F, we go to Appendix G in your textbook. And here you find your standard heats of formation, your standard enthalpies of formation as values, and you plug them in. So be aware that your Appendix G in your textbook has thermodynamic properties, which is more than just the enthalpies of formation. The enthalpies of formation are in the first column. The second and third column correspond to the Gibbs free energy of formation and the standard entropy of the compounds. Those are quantities you'll use next term when you're talking about the overall thermodynamic picture. We're just interested in the information in the first column. And always remember that if an element appears in your balanced chemical equation, Delta H naught F for any element, by definition, is 0 kilojoules per mole. So we go to Appendix G, which I've only reproduced a small portion of here, to get our enthalpies of formation. We come back with those and we plug them in. So for instance, I found the enthalpy of formation of ethanol to be negative 277.7 kilojoules per mole. And remember, phase matters, so I looked up the enthalpy of formation for liquid ethanol. For carbon dioxide in the gas phase, the enthalpy of formation is negative 393.5 kilojoules per mole. And for sucrose solid, the enthalpy of formation is negative 127.3 kilojoules per mole. Phases are a little easier with enthalpies of formation because you're always talking about the form of the molecule under standard temperature and pressure conditions. Now that I found my enthalpies of formation, the calculation is straightforward. I take 2 times negative 277.7 and I add 2 times negative 393.5. From that, I subtract 1 times negative 1,273.3 kilojoules per mole, and I get my overall enthalpy of reaction, which is negative 69.1 kilojoules per mole of sucrose for the reaction as written. So our fermentation of sucrose is an exothermic process, and it's exothermic to the tune of negative 69.1 kilojoules per mole of glucose that is fermented.